Okay, we're going to pick up with part 2 of arithmetic sequences and partial sums. We're going to look today at how we can use arithmetic sequences to model and solve real-life problems. And we're also going to finish this part of the lesson up as well. We started kind of talking about that a little bit. Actually, I don't think we talked about it at all in the previous video, but we're going to talk about that today. So there's a story about a mathematician. He's very famous, named Carl Friedrich Gauss. And there's a story that his elementary teacher was very frustrated with him. He was probably acting out. He's one of those kids, that just never stopped talking. And she got frustrated with him. So she thought, well, I'm going to get him occupied, keep him occupied for a little bit. I'm going to say, hey, Gauss, go find the sum of the first 100 integers. Now remember, this is an elementary school teacher. He's in probably second or third grade. He came back within seconds with the sum. How do you think he did that? Pause the video for a second and see if you can think about what that might have been that he did to come up with that sum. Here's a hint. He organized the numbers like this in his head. He started with 1 up to 50, counting up, and then started with 100 and counted down to 51, and he paired them up like you see here. What do you notice about every one of these sums? Well, they add up to 101. We've got a bunch of these pairs of numbers that all add up to 101, which is interesting. But what's even more interesting is how many of them will there be? Well, we see from 1 to 50, there are 50 of them, and each of those sums is 101. So if you do 50 times 101, you get the sum, which is 50, 50. And this is how Gauss quickly figured out the sum of the first 100 integers. Now, we can apply his thinking and create a formula that allows us to do this for any finite arithmetic sequence. So we know that what he was doing was arithmetic because we're adding 1 every time to get that sequence. The sequence of the first 100 integers just adds 1 to each integer to get the next integer. So it's a finite sequence, or I'm sorry, it's an arithmetic sequence. And it's finite because it only goes from 1 to 100. We can use this approach to find the sum of any finite arithmetic sequence. And these are the two characteristics that have to be true. So it has to be a finite, can't be infinite, so it has to start and stop somewhere specific. And it has to be arithmetic, so we need to be adding something or subtracting something to get the next term. That formula looks like this. So this S sub n, this just means the sum. Okay, so when you see that S sub n, it's the sum of, the n number of terms. So S sub n is the sum of n terms. Okay, so then n, we see n showing up in a few places in this formula. Here and, we'll just use that one for now. But that n is then the number of terms that you're adding together. So n equals the number of terms. We already know what a sub 1 is, and then a sub n is just our nth term. So whatever the number of terms is that we're adding together, a sub n will have the same number there for n. So the rest of those are pretty straightforward. But what we're looking at to find the sum of those terms, look at what this formula says. It says take the first term. Well, that's what we did here. The first term was 1. Take the last term in that sequence, which was 100, add them together. I added them together. And then we're going to multiply that by half the number of terms. Well, in this case, there would have been 100 terms had we looked at all of them. That's why we multiplied by 50, because we were able to pair them up. So our formula just says take the first term, add it to the last term, and then multiply by half the number of terms that you're actually finding the sum for. So let's look at this a little more closely for a few problems. So this first one, we clearly could just add the numbers together. Grab our calculator, add them together, and that would be fine. But what I want to do is figure out what the sum of those numbers is using our formula. So let's think about what's happening here. Our first term is 1. Excuse me, this is a sub 1, right? It's our first term. Let me write that down here so it's a little bit easier to see. And then we have to figure out, okay, so how many terms are there? Well, let's count, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms. So our 10th term is our 19. So to find the sum of those 10 terms, we're going to take the number of terms, which is 10, and divide by 2. And then we're going to multiply that by the first term, which we know is 1, plus the last term, which we know is 19. So that's going to give us 5 times 20, which is 100. All right, and that's the sum of those terms. So we could have probably even done it a little bit quicker if you noticed, 1 and 19 is 20. You noticed that 3 and 17, also 20, 5 and 15, also 20, 7 and 13, also 20, and then 9 and 11, also 20, and you add up 5 of those and you get 100. So it's kind of the same idea that Gauss used. All right, so the sum of the first 50 integers. Well, okay, just 50 integers, right? So our first integer, a sub 1, is just 1. Our 50th integer is a sub 50, and that's just 50. Remember, integers are just our counting numbers, and we're saying positives right now. I mean, it should say positive here. We could throw that in there, just so we know, what are we talking about the first 50 integers? We can start anywhere. The first 50 positive integers, so starting with 1 and going up to 50. So our sum of the first 50 integers using our formula will be n, which is 50, divided by 2 times the first integer plus the last integer in that sequence. So that gives us 25 times 51, which is 1275. Okay, and we're quickly able to find that sum. This is something that can save a lot of time. Obviously, to have to sit there and add up all 50 integers would take a while. 1 plus 2 plus 3 plus 4 plus 5. If you had to do that on the calculator even, it would take you forever. This just allows you to do it in a much faster way. We've already done this one, so I'm not going to do it again, but we know that's 50-50 from the example up above. So why don't you guys try this one? Pause the video, see if you can get it, and then come back and check your answer. Hopefully that wasn't too bad. So you've got the sum of the first 200 integers is 20,100, and you can see the work there. So the sum of the first W integers. Well, all right, let's talk about this. So we know the first integer is just 1. So we don't know how many integers there are, but we know we're going to go up to whatever W is. And because we're talking about integers, that's going to be just W. Write our formula out. It's the sum of the first W integers would be, well, n, which is W, over 2 times 1 plus W. Now we could multiply that out. I don't think we need to. I think it's fine just as is, but it's sort of interesting that, this formula can be applied across the board when we're talking about just the sequence of integers. So when I help you fill in the blanks here, you're going to kind of say, well, duh, Mrs. Kopp. The sum of the first n terms of an infinite sequence is called the nth, because we're talking about the sum of the first n terms, partial sum. And again, partial sum because we're not finding the whole sum of that infinite sequence. We're only finding part of the sum. We're going to use the same formula we derived above to help find these partial sums. The difference now is, though, we're going to have to do a little bit of work because we don't really have the 150th term in this situation, right? I mean, we have a few terms. We have our first term, our second term, our third term, and so on, but we only go up to our 5th term. Now, I hope that you can see that we're adding 11 to get each term in the sequence. But if we sat here and added 11 until we got to the 150th term and then went back and added all of those together, we'd be here a while. So we're going to find a way to do this in a little more concise manner, and it's going to have to use what we talked about in the previous part of this lesson. So we're going to have to come up with an equation for this. All right, so let's come up with at least an equation that represents the nth term, because that's what we need. All right, so we're going to write an equation for the nth term. So a sub n equals, all right, if you remember our equation from yesterday or 2 days ago, I guess, it was a sub 1 plus the common difference times n minus 1. Well, we've got all that information here, right? We've got a sub 1, that's 5, and we've got our common difference, that's 11. That's what we're adding each time. So I can write my equation. And my equation is going to be 5 plus 11 times n minus 1. Now, what I'm going to do here is show you another notation, another way we can write this summation out, because you'll see this in your homework, or in the problems you're going to try. So let's simplify this a little bit, right? So a sub n is 5 plus 11n minus 11. So a sub n is going to be negative 6 plus 11n, just distributing 11, combining like terms. If you remember back in our previous, last week, I think we talked about the summation notation, and that's what we're going to kind of show how this connects today. Okay, so our summation notation would write this like this. It would say find the sum, okay, find the sum from when n equals 1 until n equals 150 of the sequence that's defined by negative 6 plus 11n. And that's exactly saying what we talked about a minute ago, right? Our summation of those terms, remember that's what that summation symbol means. It means add those terms together. So it's going to be done using that formula we talked about on the front of the page here, where we take n over 2 times the first term plus the last term in that sequence. So I can do this, I can find this sum by using that formula. All right, so how many terms are we finding a sum for? Well, we're finding the 150th, so there's 150 terms. So I would say my n in my equation right here, n is 150. So this will be found by taking 150 divided by 2 times the first term. Now, we know the first term is 5. We've already found that. Plus, what we don't know is the 150th term, but luckily, we came up with this fantastic formula here that allows us to quickly find the 150th term. So all I'm going to do is I'm going to plug in 150 here. So to find the 150th term, I'm going to do negative 6, plus 11 times 150. Go ahead and figure out what that is. And you should get 1644. Okay, so that is our 150th term. Now we have everything we need. Go ahead and we're going to do 75 times 1649. I don't know about you, can't do that in my head, so let me grab my calculator. And you're going to get a rather large number here, 123,675. So that's the sum of the first 150 terms in this sequence that we were given, right? So we're not finding the infinite sum. In fact, with arithmetic sequences, infinite sums are not really something we deal with. We're always going to look at these partial sums of an infinite sequence. So there's our first one. Okay, why don't you pause the video, try part B, see if you can get it, and then come back and we'll check your answer. All right, how'd you do? Should have come up with 1,000. If you need to look at how I did this, go ahead and pause the video and look at my work, but I'll just kind of briefly talk about it. I wrote my equation for the nth term, simplified it, used that to find term 16, which was 25, wrote it out in summation form, and used my formula to actually calculate the sum. Okay, good job. Let's do one more. All right, so we're going to look at some applications of arithmetic series. We have a small business is selling $10,000, sells $10,000 worth of skincare products during its first year. The owner of the business has set a goal of increasing annual sales by $7,500 each year for 9 years. And notice it's not a percentage, which is why we can use an arithmetic sequence and not a geometric sequence. So assuming that his goal is met, find the total sales during the first 10 years that this business is in operation. So let's kind of organize our thinking here. First of all, our first term is that $10,000. Okay, that's year one. So year one, which we'll call our first term, is $10,000. Now, year two is going to be 10,000 plus 7,500. So it'll be 17,500. And we'll see that same pattern increasing, but the idea is we're adding 7,500 every year. So I want to use that information right off the bat to write my expression for the nth term. I don't want to sit here and calculate all 10 years by hand. I want to just go ahead and find the nth term. So the nth term we know is going to be the first term, 10,000, plus our common difference, which is 7,500, times n minus 1. All right, so that allows us to then go ahead and directly find the 10th term. And we do want the 10th term. I know you guys see this 9 here, and you're like, well, Mrs. Kopp, shouldn't we be finding the 9th year? Well, no, because remember, he starts at $10,000 in year one, and then for 9 years after that, he wants to increase by 7,500. So we're talking about accumulation of 10 years. So I'm going to use my formula, and I'm going to find the 10th year. So A sub 10 equals 10,000 plus 7,500 times 10 minus 1, which is 10,000 plus 7,500 times 9, which is 77,500. So that's year 10. Okay, so we've got year 1, we've got year 10. All right. Now we need to find the sum, and I'm going to use summation notation again, okay? So I'm going to say I want to find the total sum of 10 years. I want to start when we were in our first year and go up to when we hit our 10th year, and I'm going to use my formula that I created, right? So my formula that I created is right here, and I could simplify that if I want to, but I'm just showing you don't have to. It just sometimes makes it a little bit easier to read. And it's usually what you'll see when you actually encounter these problems. You're going to see it simplified. Now from there, we use our formula that we talked about up above that Gauss sort of discovered or used in his head, right? He used this idea that you take a sub 1 and a sub n, add them together, and then multiply that by half the number of terms that there actually are. So we're going to do that. We've got our first term. Sorry, let's figure out half the number of terms first. There's 10 terms that we're adding together. So 10 is n divided by 2 times our first term. We came up with our first term here is 10,000 plus our last term, which we said was year 10. So that's 77,500. And then it's just a matter of adding those and multiplying. So 87,500. And then multiplying 87,500 by 5, which gets you another rather large number. But remember, this is how much she's selling for 5 years, like total combined for all 5, or for all 10 years, sorry, combined. So $437,500 is her combined sales for 10 years. Okay, hop on Google Classroom, try a couple of the practice problems, and then go ahead and do your check-in for the day, and then we'll catch you later. Have a great day.